In this lesson, we'll cover L'Hopital's rule, which is a theorem which will allow us to solve certain limits. Sometimes this is spelled L'Hopital's like this, but in either case, it's the same theorem. Before stating the theorem, let's actually solve these two limits, and this is something that we've done before. Let's look at this one first. The limit as x approaches 1 of x squared minus 1 divided by x squared plus 4x minus 5. Our approach was, well, maybe you can just put the number 1 in place of x and get a number back. So this would be 1 squared minus 1 divided by 1 squared plus 4 times 1 minus 5. And this becomes in the top 0 over also 0. And that means, well, you can't use this method to determine the limit because we have this undefined expression. In fact, 0 over 0 is what we would call an indeterminate form. This means if your limit becomes something that looks like this, the limit may still exist and it could take on any number of different values. So the limit may still exist. Let's try to figure it out using a different method. I see that we can factor the numerator and the denominator, so let's try that. So I'll put this down here. This is equal to the limit as x approaches 1 of. The numerator is a difference of squares. You can write that as x minus 1 times x plus 1. And the denominator is also factorable, x minus 1, x plus 5. This is helpful because you can cancel the x minus 1s. And this limit is equal to the limit as x approaches 1 of just x plus 1 over x plus 5. So what we did is we rewrote it into an equivalent expression where we can put the number 1 in place of x to get our answer. If you substitute in 1, you get 2 over 6, which is really 1/3. So even though we got this indeterminate form of 0 over 0, when we simplify the limit, it was equal to 1/3, and this is the answer. We also dealt with limits at infinity, where x approaches, in this case, positive infinity. What does this limit equal? The first question you could ask is, what does the numerator and the denominator approach as x goes to infinity? Well, 2x plus 1 becomes infinite itself, and actually so does the denominator. So this is also an indeterminate form because the numerator goes to infinity and the denominator goes to infinity. So we can add this to our list of indeterminate forms. When this happens, the limit could exist and it could take on any number of different values. The approach that we use to solve something like this is to divide every single term by the highest powered x term in the denominator, which is x to the first. So it took a little bit of work, but this is the limit as x approaches infinity of, so that's 2x over x plus 1 over x divided by x over x minus 4 over x. And you can simplify some of this. I see that x's here cancel, those cancel. This gives us 2 plus 1 over x divided by 1 minus 4 over x. The point is, as x goes to infinity, 2 and 1, nothing happens to them. This goes to 0 and this goes to 0. And that means the answer is simply 2 over 1, or just 2. And you could also look at the ratio of the coefficients in front of the x terms here. So this is how we first solved limits. If we had an indeterminate form, we either had to factor or maybe manipulate the equation in some way to get our answer. L'Hopital's rule is a theorem that will apply if we run into either of these types of expressions. I will state this on the next slide. Here's a very formal statement of L'Hopital's rule. Let's say you have a fraction and you want to figure out the limit of this fraction. If both f and g are differentiable, meaning you can take their derivatives, and the denominator isn't 0 as long as you're near a, then if the limit of the top is 0 and the bottom is 0, or if the limit of the top and bottom are both infinity, then this limit here is equal to the limit of f prime of x divided by g prime of x. What this is saying is, if you look at this limit and you see either 0 over 0 or infinity over infinity, then instead of considering this limit, take the derivative of the top and bottom and try to figure out that limit. If it exists, it'll be equal to the limit that we start with. Let's try that here. Again, this is the limit we just did on the previous slide. We saw this was an indeterminate form because when we put 1s into all the x's, we got 0 over 0. Well, according to this theorem, we can look at the limit as x approaches 1 of the derivative of just the top, which is 2x, divided by the derivative of just the bottom, which is 2x plus 4. If this limit exists, it is equal to this limit. What is this limit? Here, you can actually just put the number 1 into both of the x's to evaluate it. This is 2 times 1 divided by 2 times 1 plus 4, which is 2 over 6, or a third, which is the answer we got on the previous slide. This is nice. If you have an indeterminate form like this, take the derivative of the top and bottom separately and evaluate that limit instead. Can we use that idea here as well? And the answer is yeah. If you have infinity over infinity, what you can do is take the derivative of just the top and just the bottom to get your answer. Let's see what happens here. This is the limit as x approaches infinity of. The derivative of the top is actually just 2, and the derivative of the bottom is just 1. In fact, this is just the limit as x approaches infinity of 2, and that's 2, which is the answer we got on the previous slide. So not only can this be a faster way to get to our answer, sometimes it will allow us to solve limits that we couldn't do before because certain functions aren't factorable. One final thought on this is, we're dealing with a fraction, and this says take the derivative of the top and the bottom separately. This is not saying take the derivative of the entire fraction. It's not saying use the quotient rule to get to the derivative. We look at the top and bottom separately. That being said, let's go through a few different examples. Let's see if we can use L'Hopital's rule to determine these two limits. We'll start with this one here. The limit as x approaches 1 of the natural log of x divided by x minus 1. Is this even an indeterminate form? That is, if you put the number 1 in place of all of the x's, will we get 0 over 0 or infinity over infinity? The natural log of 1 is 0, and 1 minus 1 is 0, so, okay, great. We do have an indeterminate form. That means, in order to solve this limit using L'Hopital's rule, this is the limit as x grows to 1 of, if you look at the natural log of x in the numerator, its derivative is 1 over x. The derivative of x minus 1 is simply 1. In general, a good strategy is try to simplify the expression as much as possible before moving on. There's not really much to do here, but I think it'd be better to write this as the limit as x approaches 1 of just 1 over x. We don't need this divided by 1. This is just equal to this. Now, can we figure out this limit? And the answer is yeah. We can just put 1 in place of x. We get 1 over 1, which is equal to 1. So this original limit is actually equal to 1. What about this one? The limit as x goes to 0 of sine of x over x. Again, do we encounter an indeterminate form here? If you put 0 into the function, we get sine of 0 over 0. Sine of 0 is 0, and 0 is 0, so again, here we have another indeterminate form. By using L'Hopital's rule, this limit is equal to the limit as x goes to 0 of the derivative of sine of x is cosine of x, and the derivative of x is 1. This is really just the limit as x goes to 0 of cosine of x. Can we simply put 0 in place of cosine? Sure. What's cosine of 0? It's also 1. Let's again use L'Hopital's rule to figure out these two limits. They are both limits at infinity, so we'll start with this one here. The limit as x approaches infinity of e to the x divided by x squared. Now, e to the x itself goes to positive infinity, and so does x squared, so this is certainly of the form infinity over infinity, which is an indeterminate form. Therefore, we can take the limit as x approaches infinity of the derivative of the top divided by the derivative of the bottom, which is e to the x over 2x. Now, if this limit exists, it should be equal to this limit here. So what happens to this expression as x goes to infinity? Well, e to the x still goes to infinity, and 2x goes to infinity as well. So this is actually also of the form infinity over infinity, which is an indeterminate form. What does that mean? It means this process can continue. Anytime you encounter an indeterminate form, you can use L'Hopital's rule again. So that's what we'll do here. So I'll continue my work down here and say, all right, well, this should be equal to the limit as x goes to infinity of, if you take the derivative of the top, you get e to the x, and then the derivative of the bottom is just 2. Now, can we determine what this limit is equal to? So the top goes to infinity, and the denominator was actually just 2 this time. This is no longer an indeterminate form because as a fraction, sure, the top is infinity, but the bottom is not. In fact, that is enough to say that this limit does go to positive infinity. I mean, technically the limit doesn't exist, but it's always getting larger and larger and larger, so we no longer have an indeterminate form. But what that means altogether is that this limit has to be the same as this limit, which is equal to positive infinity. Before moving on to this example here, just something to think about. What if this was the question, the limit as x goes to infinity of x squared over e to the x? What would the approach be for this? Well, we still have an indeterminate form because we have infinity over infinity. By L'Hopital's rule, you can say this is the limit as x goes to infinity of 2x over e to the x, just like before. Again, we have an indeterminate form, so we can use L'Hopital's rule again and say, all right, this is the limit as x goes to infinity of 2 over e to the x. What does this limit equal in this case? 2 stays 2, but e to the x goes to infinity. A number over something going to infinity, we can conclude, goes to 0. It's good to compare these two ideas. So infinity over a number becomes infinite, but a number over infinity goes to 0. All right, let's compare this to this example here. The limit as x goes to infinity of 8x squared plus 2x plus 1 divided by 1 minus x minus 4x squared. This is also an indeterminate form. Here, 8x squared goes to positive infinity. Here, a minus 4x squared goes to negative infinity. So if you want to think about the type of expression this becomes, it's positive infinity over negative infinity. But whether it's positive or negative, this part here is still an indeterminate form. And therefore, we can use L'Hopital's rule to solve this limit. So this limit is equal to the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom, which is 16x plus 2 divided by negative 1 minus 8x. The question is, can I simply just evaluate this, or is this still an indeterminate form? And it still is indeterminate. The top goes to positive infinity, the bottom goes to negative infinity, but this is really an infinity over infinity situation, meaning we can use L'Hopital's rule again. This is the limit as x goes to infinity of, the top is 16, the bottom is negative 8. This limit is 16 over negative 8, or simply negative 2. So up to this point, we've encountered two different types of indeterminate forms, a 0 over 0 or an infinity over infinity. There are others. We could have something of the form 0 times infinity, and that will be an indeterminate form too. Let's see why this is the case by looking at this first example. What is the limit, as x goes to 0 from the right, of x times the natural log of x? Well, first of all, this isn't a fraction, so you can't have 0 over 0 or infinity over infinity. But this expression will look like this. Let's just carefully examine that. If you look at just the x goes to 0 as x goes to 0, so you can put a 0 here. But what happens to the natural log of x as x goes to 0 from the right? Maybe just as a guide, here is a graph of the natural log of x. And we're asking, what does the y values approach as x goes towards 0 from the right? There's a vertical asymptote on the graph, and it's going towards minus infinity. So your limit will start to look like this. Now, there's a negative here, but of course, you could factor it out. The important part is, well, our limit has a negative, but there's a 0 times infinity. And you can't say that this is infinite, and you can't say that it's 0. In fact, it could potentially be any real number. Let's see why that happens. The goal to use L'Hopital's rule on a question like this is to rewrite it so you actually see a fraction. This rule requires that there be a fraction in your expression. There's a simple way to do it for this problem. This is the limit as x goes to 0 from the right of. I'm going to leave the natural log of x alone in the numerator. If you want to put this x into a denominator, you can make the exponent on this case negative, like this. This is now a fraction, meaning you could potentially use L'Hopital's rule on it, and it's equivalent to this, because you could bring this x back up to the top and make the -1 a +1. Depending on what type of notation you like to use, you could also write this as a fraction within the denominator. I'll just put that next to it here. This is the very same problem as the limit as x goes to 0 from the right of the natural log of x divided by 1 over x. So this and this are in fact the same. If we want to use L'Hopital's rule on this, now that it's a fraction, we have to have either 0 over 0 or infinity over infinity. Do we in this case? Well, we already know the top goes to negative infinity. So this is of the form negative infinity in the numerator. What does x to the -1, or 1 over x, go to as x goes to 0 from the right? You again could refer to a graph just as a quick guide. Here's a graph of 1 over x. As we approach 0 from the right, the function heads up towards positive infinity. Therefore, this is the denominator. This is an indeterminate form, an infinity over infinity. If you have a 0 times infinity, you can always create a fraction where you either get 0 over 0 or infinity over infinity. And that's why this is an indeterminate form. Let's now use L'Hopital's rule to figure out, well, what does this simplify to? Okay, by L'Hopital's rule, this is the limit as x goes to 0 of, well, from the right of, the natural log is 1 over x, and x to the -1 is negative x to the -2. If we simplify this, this is the limit as x goes to 0 from the right of. I can bring this x to the -2 to the numerator. I can also pull this negative outside of the limit. Here's what I end up with. Maybe I'll make just a little bit of more space for this. I'll remove the constant, which is the negative, from the limit. I have 1 over x in the numerator. I'm bringing this whole thing to the top, so it's x to the +2. The entire denominator is now a 1, which means I don't have to write it. We have this. What does this limit equal? Well, x and x squared, we can cancel an x to just call this x. This is negative the limit as x goes to 0 from the right of just x, and that is equal to 0. So overall, the answer to this limit is 0. It was a product. I wrote it as a fraction, applied L'Hopital's rule because we had an indeterminate form, and I found my final answer. Let's try this process again in a similar example, but this one is a limit at infinity. What is the limit as x approaches infinity of x times sine of pi over x? Again, is this something of the form 0 times infinity? Let's see. As x goes to infinity, the first part here becomes infinite, so that's a good start. This is an infinity times. What happens to sine of pi over x as x goes to infinity? Pi over x goes to 0, so this is sine of 0. And sine of 0 is 0. So this is a 0 times an infinity, which is an indeterminate form. To use L'Hopital's rule on this problem, I'm going to re-express this as a fraction, much like what we did in the previous problem. This is the limit as x goes to infinity of. I think I'll leave sine of pi x in the numerator. I'm going to write it as pi x to the -1. And in the denominator, I'll put x to the negative 1. So going from here to here, I took x, made it an exponent of negative 1, and moved it into the denominator. Here we have pi over x, and I thought we'd better write this as a product, so I moved the x to the numerator and gave it a negative 1 exponent. Before moving on, you could, again, think of this as the limit as x goes to infinity of sine of pi over x divided by 1 over x, if you prefer to think of not negative exponents but fractions. Is this an indeterminate form? Well, the numerator goes to sine of 0, and sine of 0 is 0. And the denominator, as x goes to infinity, 1 over x also goes to 0. And what do you know? If you have a product that is infinity times 0 and you write it as a fraction, this time it's 0 over 0. It could be infinity over infinity, but in either case, that is an indeterminate form. I will now use L'Hopital's rule to figure out what this limit is equal to. This is the limit as x goes to infinity of, the derivative of the numerator is cosine of pi x to the negative 1, and by the chain rule, it's negative pi x to the negative 2. In the denominator, the derivative of x to the negative 1 is negative x to the negative 2. Notice we can simplify a bunch of stuff here. The negatives cancel, and the x to the negative 2's cancel. I am left over with this pi, but we have that this is the limit as x goes to infinity. I'll put this as pi times cosine of, and I'll write pi over x. As x goes to infinity, pi over x goes to 0. This is pi times cosine of 0. And what's cosine of 0? It's 1. And this means the entire answer is pi. Just to recap, this was a product, but it was an indeterminate form. I wrote it as a fraction, which was also an indeterminate form, but as a fraction, we can apply L'Hopital's rule. After I simplified it, I had this expression here. This was no longer an indeterminate form, so I merely thought that this goes to 0, cosine of 0 is 1, and pi times 1 is just pi. So far, we've encountered the following indeterminate forms: 0 over 0, infinity over infinity, 0 times infinity, but are there others? And the answer is, well, yes. You could have something that is infinity minus infinity. The reason this is also an indeterminate form is you can manipulate it in a way so it refers back to one of these three. Let's see that in this example here. What is the limit as x approaches 1 from the right of 1 over the natural log of x minus 1 over x minus 1? To start with, here we have a difference of two functions. Will we get something that is of the form infinity minus infinity? Let's look at each piece to figure that out. What's going on with 1 divided by the natural log of x? To show that this goes to positive infinity, I think it will be enough just to graph the natural log of x itself, locate what happens at 1, and go from there. The natural log, just the denominator, if we're approaching 1 from the right, is heading towards 0, and those numbers are positive. That means 1 divided by something which is 0 goes to infinity. So we have 1 over the natural log of x as we approach 1 from the right is going to positive infinity. Now, what about this? 1 divided by x minus 1. I think I'll actually just look at a graph of this whole thing. I'll put that over here as well. So this is the function 1 over x, but it's shifted one place to the right. So we have a function that looks like this. This is y is equal to 1 over x minus 1. As we approach 1 from the right, this is going up to positive infinity. So this is approaching infinity as well as we get closer and closer to 1. So what does this mean? This expression is of the form infinity minus infinity. This indeterminate form, to use L'Hopital's rule, we have to write it as a fraction, like this or this. Let's go over how that will be done. This is the limit as x approaches 1 from the right of. I'm going to combine this into a single fraction. My least common denominator is the natural log of x times x minus 1. So I have one fraction. I'll write x minus 1 times the natural log of x. That means we're multiplying this fraction by x minus 1 on the top and the bottom. So 1 times x minus 1 is x minus 1. And this fraction, we're multiplying by the natural log of x, which is the natural log of x over the natural log of x. So this is our fraction, a single fraction. Is this also an indeterminate form of either this form or that form? Well, let's see. If we put 1 into the numerator, we get 1 minus 1, which is 0. And the natural log of 1 is 0 as well. So this is 0 in the numerator. And if we put 1 into the denominator, 1 minus 1 is 0. The natural log of 1 is also 0. So this is 0 over 0. This is an indeterminate form because we can convert it into something that is a fraction and an indeterminate form. We can now use L'Hopital's rule to solve this limit. This is the limit as x approaches 1 from the right of. The derivative of the numerator is 1 minus 1 over x. For the denominator, I think we have to use the product rule. The derivative of the first is just 1, which I won't write, and then we copy down the second, which is the natural log of x, plus, now we leave the first alone, which is x minus 1, and the derivative of the natural log of x is 1 over x. So this is equivalent to this through L'Hopital's rule. Can we now plug 1 in place of the x's to figure out the limit? And the answer is, well, no. But we do get another indeterminate form. If you put 1 in place of this x, you get 1 minus 1, which is 0. And if you put 1 into the denominator, the natural log of 1 is 0. This is 1, but 1 minus 1 is also 0. And so, okay, we get 0. I think what I'm going to do before applying L'Hopital's rule again, I'm going to multiply every single term by x. If we do that, this is the limit as x approaches 1 from the right of. So in the top, we'll have x minus 1. In the denominator, we'll have x times the natural log of x. And then we'll have x times this thing is just 1. We'll be left with x minus 1. And I don't need the parentheses on that anymore. So from here to here, I multiply by x over x to cancel the fractions within the fraction. We still have an indeterminate form. Putting 1 in place of all the x's yields 0 over 0. But that just means we'll use L'Hopital's rule again. This is the limit as x approaches 1 from the right of. The derivative of the top is 1. In the bottom, okay, we have to use the product rule on this part here. So we'll have 1 times the natural log of x. I'll just put the natural log of x. Plus the first times the derivative of the natural log, which is 1 over x. Then the derivative of x is 1, and 1 goes to 0. I'll write this as just 1. This is the limit as x approaches 1 from the right of 1 divided by the natural log of x plus this is 1, this is 1, we get 2. All right, can we now just substitute 1 in place of this x to get our limit? And the answer is yeah. The natural log of 1 is 0. We'll have 1 divided by 2, and so we get a half. So this is the final answer. If you have infinity minus infinity, the answer actually is not always 0. The answer can be anything because it's an indeterminate form. The trick is rewrite this so you get a single fraction so you can use L'Hopital's rule to get the answer. Before attempting to solve our last example, I want to list out the last 3 indeterminate forms that we can encounter. And those all have exponents. Things of the form 0 to the 0, 1 to the infinity, and then infinity to the 0. Any expression like this that appears within a limit will also be an indeterminate form. And the question is going to be, well, why is that the case? And the answer is going to be because you can always trace these back to either a 0 over 0, an infinity over infinity, or really a 0 times infinity. And the way that you would do that is by using a natural logarithm. Let's examine this here in example 4. So to solve this limit, the limit as x goes to positive infinity of 1 divided by 9 over x to the x power, what happens to this expression as x goes to infinity? Well, there's an exponent of just x, so we get an infinity in the exponent, and 1 plus 9 over x, 9 over x goes to 0, leaving just 1 inside the parentheses. So this thing starts to look like a 1 to the power of infinity. Now, why would this be an indeterminate form? I'll put that over here. If you have 1 to the power of infinity, you'll introduce a logarithm, in this case, the natural log. Now, we have a property of logarithms that says you can bring that infinity down front, like this. So basically, 1 to the infinity will be equivalent to the natural log of 1 to the infinity, which is equivalent to infinity times the natural log of 1. And what's the natural log of 1? It's 0. You can convert this into this, which is an indeterminate form. The trick will be if you see an exponent and you're asked to use L'Hopital's rule, we're going to start by taking the natural log of this expression. Here's what this problem looks like. We have the limit as x goes to infinity of 1 plus 9 over x to the power of x. I'm going to assume this limit exists and is equal to, let's say, L. I don't know what it is, but my goal is to find L. What I'm going to do next is take the natural log of both sides of this expression. We have the limit as x goes to infinity of the natural log of 1 plus 9 over x to the power of x, and that's equal to the natural log of L. I'm now going to work with this expression and hopefully use L'Hopital's rule to figure out this limit. I'll get a number for this thing, and it will be equal to not L, but the natural log of L. So let's focus on just this part. I'm going to take this x and bring it down front. So this changes the problem to, this is the limit as x goes to infinity of x times the natural log of 1 plus, and maybe I'll write 9 over x as 9 times x to the negative 1. This isn't a fraction, but we can make it a fraction by putting this into the denominator. So this is equal to the limit as x goes to infinity of the natural log of 1 plus 9 times x to the negative 1, all divided by x to the negative 1. Now check this out. As a fraction, is this of the form 0 over 0 or infinity over infinity? The answer is yeah. This goes to 0, so we have the natural log of 1, which is 0. 1 over x goes to 0 as well. This is a 0 over 0. So this fraction is of the form 0 over 0, and that means we can use L'Hopital's rule to solve it. By L'Hopital's rule, this is the limit as x goes to infinity of, the derivative of the top is 1 over this thing. So that's 1 over 1 plus 9 times x to the negative 1 times the derivative of the inside part. 1 goes to 0. This goes to negative 9x to the negative 2. So I'll put negative 9x to the negative 2. This is all divided by the derivative of just the denominator, negative x to the negative 2. A lot of stuff cancels. This negative cancels with that. The x to the negative 2 cancels with the x to the negative 2. This entire denominator is 1. 9's left over. I don't need this fraction anymore. It's divided by 1. I'll just write down this. I'll include the 9. And in fact, I'll put the 9 here. This is the limit as x goes to infinity of 9 divided by 1 plus, and I'll put 9 over x. So again, what happened here is I canceled the negatives. I canceled the x to the negative 2's. The entire denominator was 1, so I didn't write divided by 1 here, just left it off. I then took this and multiplied by 9, which put 9 in the numerator, and I decided to write this x to the negative 1 as 9 over x. Can we figure out this limit? Yeah. 9 goes to, well, it stays 9, and so does 1. But 9 over x goes to 0. This is 9 divided by 1 plus 0. This equals 9. We did not solve the original question. We solved this one. We showed that this was equal to 9. That is equal to the natural log of L. So I'm going to put that down here. The ultimate goal was, okay, I wanted L, not the natural log of L. How do I get L? My equation is 9 equals the natural log of L. I can take both sides and put them in the exponent of e. You'll have e to the 9th and e to the natural log cancel to leave us with just L. This is a long way to say L is equal to not 9, but e to the 9th power. And this is the final answer.